You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So we've talked about dark matter on our show a couple times by now, but there are just so many interesting questions to ask around it that, well, here's another episode. So the deal is that the universe appears to be filled with some kind of invisible matter that we call dark matter, but physicists don't actually know what this stuff is. We do know that whatever it is, it can't interact with light very much, otherwise we would have seen it by now. And if you think about the objects that we know about existing in space, which don't interact with light very much, you may think of black holes. You may have heard of black holes before, but basically, they are these extremely dense objects with gravitational fields so strong that not even light can escape. Black holes don't let any light out of their gravitational grasp, and so there's no way to actually see them. We can only see how they gravitationally affect the objects around them. Could black holes possibly be the dark matter? In today's episode, we'll see that the answer to this question is actually maybe, but probably not the kinds of black holes you've ever heard of.
So black holes are one of the more wild and exotic consequences of Einstein's theory of general relativity. So in a nutshell, what Einstein's theory says is that when you put matter or energy in space, it changes the geometry of the space and time around it. It warps or curves or distorts the space and time. And the thing that we've been calling gravity for hundreds of years is really just the consequence of that space and time being warped in this way that causes things to move through it differently than it would if that mass or energy hadn't been there.
And the more mass there is in a particular spot, the more space around that spot will curve and warp. That's why gravity is so much stronger around a big object like the Earth than around a small object like you or me.
And it turns out that if you put enough matter or energy in one place and make it compact enough, you will warp the surrounding space so dramatically that even light can't escape from that object. So we say that thing is surrounded by something called an event horizon, sometimes also called a Schwarzschild radius, and it is an entirely one-directional causal barrier. Like nothing inside of it can ever get out. Things can fall in, depending on your frame of reference, but basically everything that gets into a black hole is trapped inside of that black hole.
So to make a black hole, you have to take some mass and squeeze it into a tiny enough area that it's smaller than the space described by its Schwarzschild radius. For example,
if you took something with the mass of the sun, in order to make it into a black hole, you'd have to squeeze it to a radius of smaller than about 3 kilometers. So from 700,000 kilometers down to 3. So you really have, you have to compress something like the sun a radical degree to make it into a black hole. Something like the Earth, you'd have to squeeze down into a radius of something like a centimeter. So you don't find black holes out of ordinary material very much, but when you have really big stars, 30 or more times as massive as the sun, these things ultimately will collapse and form black holes.
Yeah, the analogy I like is that you have to squeeze the mass of the Earth into the size of an acorn.
I always heard marble, but sure, yeah.
Yeah, I like acorn because I guess it's relating to Earth.
Perfect.
So when theorists like Stephen Hawking and Roger Penrose were first thinking about black holes in the 1960s, it kind of felt like they were maybe just a theorist's crazy idea, like something that wouldn't actually exist in nature.
But in the early 70s, astronomers started to actually see evidence for these things for the first time. In particular, they were looking at this thing called Cygnus X1, which is a really bright source of X-rays. This had been observed earlier, like in the early 60s, but by 1972, it had started to become clear that this thing was probably a black hole. What it really is a big giant star, a blue supergiant, with a black hole just about 20% of the Earth's sun distance away from it. So it's a really close neighbor. And that black hole is sucking matter from the big blue supergiant and creating something called an accretion disk and shooting out energy in the form of jets and producing a ton of X-rays. We know today that this thing's about 15 times as massive as the sun, and it's too small to be any kind of normal star. It couldn't even be a neutron star. This thing is almost certainly a black hole. Since then, we've discovered a lot of other X-ray signals that we think are black holes. We've also discovered supermassive black holes in the centers of most galaxies. For example, in the middle of the Milky Way, there's a black hole called Sagittarius A star, and it's about 4 million times as massive as the sun. We know how massive it is because we can look at stars, other stars, just like zipping around it at super high speeds, and you can work out almost exactly where it is and how heavy it is or how massive it is. In recent years, we've also observed gravitational waves from black holes merging. Here I have in mind the LIGO experiment. This started back in 2015, or at least the first detection was in 2015. And they observed the ripples in space and time that are produced when black holes and other compact objects merge into one another. And then even more recently, just last year, something called the Event Horizon Telescope produced the first image of a black hole. In particular, this is the image of the black hole in the heart of M87, this kind of nearby galaxy. It's about 7 billion solar masses, so wildly larger than the one in the center of the Milky Way. And when I say it's an image, you can't see the black hole itself, but it's an image of the gas just at the edge of the black hole's event horizon. It's a really spectacular step forward.
Okay, so black holes are definitely cool. That's been established. But could they make up the dark matter?
There's a lot of evidence that black holes exist, and there are even lots of them in the universe. But none of the kinds of black holes that we've ever observed are likely to make up any appreciable fraction of the dark matter. We know a lot about our universe and how it's evolved over time. And by looking at the light element abundances that were formed in the first seconds and minutes after the Big Bang, and by looking at the light that was produced when the first atoms were formed a few 100,000 years after the Big Bang, we have a very accurate measurement of how many protons and neutrons and electrons there are in our universe. And there's just no way you could take those protons, neutrons, and electrons and combine them in some way to make enough dark matter. So all these stars and things that go on to form black holes, those black holes are ultimately produced when you cram enough protons, neutrons, and electrons together, and there just aren't enough. There aren't enough building blocks. So these sorts of black holes can't make up an appreciable fraction of the dark matter.
So the short answer is no. Black holes probably don't make up very much of the dark matter. Like Dan said, there just isn't enough normal matter in the universe to form enough black holes to make up all of the dark matter. But it turns out that there are other exciting theoretical ideas that may be able to get around this.
You could imagine that maybe there were some kinds of black holes that formed even earlier in our universe's history. So before the first seconds and minutes, and you would call these things primordial black holes. And this is an idea that goes back to 1974 with Bernard Carr and Stephen Hawking. And they started to argue that just maybe we could have had a lot of black holes in the early universe. And if those black holes were in the sort of right mass range, maybe they could still exist in large numbers today. And maybe they could make up all or most or all, a lot of the dark matter.
So primordial black holes are notably different than the kinds of black holes we were talking about before. The black holes that we know about, they formed from the death of giant stars. But primordial black holes, they would have formed in the very early universe before there were any stars. But in order for that to happen, the universe would have to be lumpy enough. It would have to have regions that were more dense than other regions, so that the dense regions could collapse due to gravity into these black holes. And that may not have been the case.
After all, when we look at the cosmic microwave background, that light that was produced only a few 100,000 years after the Big Bang, we see a very, very smooth universe, one with the same energy density just about everywhere, to 1 part in 10 to the 5. And a smooth universe is not a universe that makes a lot of black holes. To have black holes, you need to compress a lot of energy into a really small space. So it doesn't, the universe that we see in the cosmic microwave background isn't one that looks like the sort of universe that would have a lot of black holes. But when we look at the cosmic microwave background, we're really looking at kind of our universe with broad brush strokes. We don't see the fine resolution. And it's at least possible, who knows, that there might have been much smaller regions than we can currently probe that were really dense. So maybe things were really smooth on large scales with big density spikes here and there in the universe, and those could have at least hypothetically made the kind of black holes we're talking about here.
And using some really cool theoretical ideas, we can actually set limits on the size of these primordial black holes, basically how big or small they're allowed to be. And how big primordial black holes are allowed to be is determined by an idea called the cosmic horizon. Basically, since the universe is expanding, there's a limit to how far away you can be from something while still being able to communicate with it.
So right now, Shalma, you're in Hyde Park and I'm in Oak Park, both pretty close to Chicago. If I send a beam of light to you, it'll arrive in a fraction of a millisecond. But now let's say space is expanding between us so fast that in that millisecond, a fraction of a millisecond, the distance between you and I double. And then, my light beam still has some distance to reach you, but by the time it gets halfway to you again, the space is doubled again, and it will never reach you. If space is expanding fast enough, you and I would be causally disconnected. Our horizons would not extend to each other. And in the early universe, our universe was expanding very, very fast. So there were relatively small horizons, and the biggest possible black hole, the biggest possible amount of stuff that could collapse into a black hole is whatever would fit inside one of those horizons. So, for example, right around the time that the light elements started to form, about a second or so after the Big Bang, a horizon would have contained about 10 to the 35 kilograms, or maybe like 50,000 times as much mass as the sun. So that's kind of the very biggest primordial black hole anyone could ever consider being a realistic possibility. But probably they're much smaller. For example, if those black holes formed at the sort of times that the Large Hadron Collider is currently exploring the laws of physics for, those would be more like 10 to the 23 kilograms or 10 to the minus 7 solar masses, just smaller than the Earth.
And to observe primordial black holes, we would have to observe their gravity affecting objects around them. And we can do this with a technique called gravitational microlensing.
And the idea here is that you could look at something like a star, and if a black hole happened to lie almost precisely between you and the star, that black hole's gravity will deflect the light from the star around it, making that star seem brighter for a while that alignment is really good. If you have something like a 100 solar mass black hole, something 100 times as massive as the sun, that deflection, that lensing could go on for about a year or so. And if you instead had something about the mass of the Earth, that lensing would only go on for a few hours. So roughly speaking, gravitational microlensing can be used to study or look for black holes as heavy as hundreds of solar masses down to maybe a billionth of a solar mass or so. But even if all of the dark matter, 100% of the dark matter were made of black holes, only about 1 in 2 million stars would be lensed at any given time. So you can't just look at 1 or 2 or 10 or 100 stars and hope to ever see this. So what you have to do is to simultaneously look at a very large number of stars all at once, and then monitor them for months or years or even longer, hoping to find evidence that black holes are microlensing this population of stars. In the 1990s, collaborations like Macho and Eros and others started to do this. And over the years, they saw some events like this. They saw some things that very much look like black holes, maybe not primordial, but some black holes all the same. And they had a few dozen microlensing candidates. And this was very exciting for a while. But ultimately, we found out that the black holes in this sort of mass range can't make up more than a few percent of the dark matter. So maybe there's some black holes that are contributing to this, but they're certainly not the bulk of the dark matter.
And gravitational microlensing rules out primordial black holes with masses over 10 to the minus 10 or 10 to the minus 9 solar masses, basically a tiny, tiny fraction of the mass of the sun. So if primordial black holes do exist, they have to be really small.
So let's take it from the opposite direction and say, like, what's the smallest black holes we could be considering here? And to do that, we have to talk about a phenomena called Hawking evaporation. So this is probably Stephen Hawking's most famous discovery, or at least one of his greatest hits. And what he showed back in the 60s and 70s is that if you take a black hole and look at its surface, you'll find that that surface radiates like a hot object. This is super surprising. You would think, I in this podcast, I even said before, nothing can escape from a black hole. But it turns out that because of the laws of quantum mechanics, even the surface of a black hole radiates light and other kinds of particles. So roughly speaking, and this is an imperfect analogy, but it kind of gets the idea across. Right around the event horizon of a black hole, you could imagine a particle and its antiparticle spontaneously popping into existence. This is the sort of thing that quantum mechanics tells us can happen and happens all the time. And if it happens, in the room I'm sitting in right now, that particle and its antiparticle will just annihilate an instant later, and you'll be back to where you started. But if this happens near an event horizon, it's possible one of those particles will fall back into the black hole, and the other one will be left outside of the black hole, outside of the event horizon, and it won't be able to annihilate. So that means it will radiate away. And since the black hole is effectively creating new particles this way, it slowly loses mass. It slowly evaporates over time. Now, the kind of black holes we know exist, like the kind that are left after supernovae or the kind that you find in the middle of galaxies, these things evaporate really, really slowly. They haven't lost any appreciable fraction of their mass over the history of the universe. But small black holes can evaporate a lot more quickly. For example, if you had a black hole that was about 10 to the 15 grams, it will evaporate in like 10 to the 12 years or 100 billion years. And so that means that so far they might have lost an appreciable fraction of their mass. So we know that since there's the same amount of dark matter approximately today as there was 10 billion years ago, that you can't have most of the dark matter be made up of black holes lighter than about 10 to the 15 grams. They would have evaporated too much by now if they were.
So, primordial black holes that small may not be able to be the dark matter, but they're still an interesting thing to study.
I write papers and do research on super light black holes that would have evaporated, very early in the universe's history, or maybe even later. I just wrote a paper with some of my collaborators about black holes that might have evaporated in the first 100,000 years after the Big Bang. So these aren't dark matter, but they're still pretty interesting, and they can have a lot of interesting consequences for the early universe. They could have produced the dark matter as Hawking radiation, which is a pretty cool possibility. They might have made something that we call dark radiation. They could have played a role in explaining the matter-antimatter asymmetry of our universe. It could have done a lot of cool things, despite not being a solution to the dark matter problem directly.
Oh, wow, that's interesting. The producing dark matter as Hawking radiation.
Well, that's the thing about Hawking radiation. It's really just gravity doing the work, which means that it will produce all kinds of matter, no matter how weakly interacting it is. So it's kind of a natural way to produce something that you can't easily detect. Yeah.
But anyway, back to primordial black holes that could possibly be the dark matter. So we talked about using the idea of Hawking radiation to rule out primordial black holes that would evaporate too quickly, but we can also search for the Hawking radiation itself.
In particular, as a black hole continues to evaporate and lose mass, it gets hotter, so it radiates particles with more and more energy. And by looking for gamma rays and other sorts of energetic particles that might be produced from Hawking evaporation from black holes, we can rule out black holes with masses up to about 10 to the 17 grams as being all of the dark matter. So when we take all this together, gravitational microlensing tells us that if black holes make up all the dark matter, those black holes have to be lighter than about 10 to the 23 grams. And if from Hawking evaporation, if black holes make up all the dark matter, they have to be heavier than about 10 to the 17 grams. So you have this window between about 10 to the 17 grams and 10 to the 23 grams where maybe all or most of the dark matter could be black holes. Now, to put this in context, 10 to the 23 grams is lighter than any of the planets in the solar system, but it's bigger than the biggest asteroids. So these are big objects, but subplanet-sized or massed objects.
And there are lots of ideas about how we could look for primordial black holes in this mass range.
We look at systems called globular clusters, which are basically clusters of stars tightly gravitationally bound to one another. And it's been argued that if black holes were all the dark matter, those black holes would have, the gravity of those black holes might have disrupted some of these star clusters. And since we see these clusters and they remain bound and behaving the way they do, people have argued that certain mass ranges of black holes might be disfavored or ruled out. But other people disagree. It's kind of complicated, and frankly, there's not a clear consensus on that yet. People have also looked at binary systems where there are two stars gravitationally bound to each other. If those stars are bound but still pretty separated from each other, we call these wide binaries, then you could imagine they might have been torn apart if they had passed by a black hole. So you can, again, set upper limits on how many of these black holes there might be. People have also talked about the effect of large numbers of black holes on things called neutron stars and white dwarf stars. If a black hole were to be gravitationally bound to one of these stars, it might accrete matter onto the black hole, causing it to gain mass. And this would mean that those black holes that started out in this interesting mass window, the 10 to the 17 to 10 to the 22 grams, would gain mass moving into the higher mass range where we could look for them. So we're back to the gravitational microlensing constraints in that case. All of these constraints I've just mentioned are pretty controversial and hotly debated in the literature. I think probably they're pretty compelling that a lot of this mass range has been explored, but it also seems entirely possible to me that there might be some holes in this net that would allow for at least the possibility that primordial black holes can make up all the dark matter in parts of this mass range.
But really, all of these ideas about primordial black holes are very hotly debated by physicists. Right now, they're more of a fun theoretical idea than something most physicists have a lot of faith in. Even a lot of the mass constraints that we've been talking about could be up for scrutiny.
Some of our constraints are really bulletproof. Like I think the gravitational microlensing ones over most of the mass range are. And I think the Hawking radiation ones probably are. But these ones in the middle, they're barely strong enough to rule out the things they're interested in. And they have a bunch of assumptions, and they have, it's complicated. And if the experts can't agree, then I'm not going to figure out the right answer just for the sake of a podcast.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jay Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.